Hello, my name is Frank Ferro. I'm the Senior Director of Product Management at Rambus, responsible for high-speed memory interface IP. Artificial intelligence is driving the need for higher memory bandwidth across the internet. If we start at the cloud and the data center, it's very high bandwidth requirements in order to do AI training. Now, AI training is where you take a neural network and you're going to put lots of data into that network in order to recognize certain images or data patterns. And so these typically take terabytes of memory bandwidth. Once these networks are trained, then they can be pushed out into the network to the edge or even to the endpoints of the network. Now that pushing these models out takes takes higher speed links, so higher speed SerDes. It also takes power in the data center. So the ability to not only process in the data center, but also to do AI at the edge of the network or even at the endpoints of the network is important. It takes some of the load off the data center. So we see in 5G base stations, they're also doing AI training and inference right in the base station or inline processing. This does relieve some of the need to go up into the cloud and the data center, but it does push a lot of the memory bandwidth and higher speed processing requirements into the edge. And so there you see maybe a little less than data center, but still, 500, megabytes of memory bandwidth requirements. And if you look at the edge of the network, the endpoints of the network, applications like automotive also take a very significant amount of bandwidth, because here you're trying to recognize street signs, or you're trying to recognize pedestrians, and so these networks have to be very accurate with lots of data to train them. They have to work in real time because you're driving in a car. So again, all of these types of applications are driving the need for much higher memory bandwidth across the internet. So given the need for this additional memory bandwidth to run these AI neural networks, what does that really mean from a compute architecture standpoint? So today you see CPUs and GPUs that are running the neural networks, and they're doing a good job. And this is really the bulk of where we're seeing the processing being done. But as these networks mature and become more specialized, we're seeing new architectures emerging that are going to take advantage of the specific problems we're trying to solve. So if they have a specific application, we see ASICs being developed to go address those applications. And in these cases, they can customize the processor and the memory bandwidth to solve the specific problem. So we're seeing higher levels of efficiency with these new processors. And of course, these new processors are looking to the memory subsystem, where we're seeing a lot of the bottlenecks, and how can they improve that memory subsystem and open up that bottleneck in order to kind of get the overall performance you're looking for. Now let's take a look at some of the specific performance numbers on these memory systems. And first, I apologize, this is a little bit of an eye chart. At the next slide, we'll take another look at this data. Hopefully it'll be a little clearer. But you can see along the top from just the raw bandwidth numbers that HBM gives you the highest bandwidth with 3.6 terabits per second of processing, so a significant amount of processing power. But as I mentioned, you can see the number of interface bits is 1024. So relatively low speed, still running at only 3.6 gigabits per pin rate, but by making a very wide interface, you're getting extremely high bandwidth. If you look at GDDR, again, still very high bandwidth, 512 gigabits per second at a 16 gigabit per pin. So this has the highest rate per pin, but you're only using 32 bits on the interface. And then from DDR is still your lowest cost memory, but also your lowest bandwidth memory. So these are some of the trade-offs, and you can see LP DDR5 is now kind of catching up a little bit, 6.4 gigabits per second for LP. So as I mentioned, these are very good for some of the AI at the edge, and as you get into the data center, accelerator cards for inference, GDDR6, and HBM for AI training. And then just from a complexity standpoint, You can see that again, as I mentioned, HBM has the highest complexity because you have this 2.5D manufacturing process, and the other memory systems are more typical where you solder them down on a PCB. The other good thing about HBM is the power efficiency. So because you're running it slow and wide, you still have very good power efficiency, which is also a nice attribute. So you have very small area with HBM, you have high bandwidth, you have good power efficiency. Excuse me. Now I'd like to take a deeper dive into two of Rambus's memory subsystem solutions. First, I'd like to look at HBM, and then we'll look at GDDR6. So if you look at the block diagram here, you can see the memory subsystem solution offered by Rambus. So the subsystem provides a complete validated memory system interfacing to your ASIC through, say, for example, an AXI bus, and then the controller to the PHY out to the DRAM. So what you see here in blue is a fully validated memory subsystem that Rambus customizes to your specific application. We start with the memory controller. You can see these light blue blocks are optional blocks that are customized based on the requirements and on the type of application. This is delivered as a soft IP or configurable RTL. And then the PHY is delivered as hardened IP. And what that means is that we deliver a GDS block that, again, is configured for the system that you're implementing. So in order to harden that block, we have to understand the channel, the interface between the memory and the DRAM. We have to understand the physical design, the board, the package. And so we work very closely with customers to make sure that the PHY conforms to the system. We call this kind of a co-design or right by design methodology. And this is delivered as fully integrated, validated block. In addition to the IP, we provide all the testing available for system bring up, and even in the early stages of design, we provide test benches so that you can do simulations and get started on the design very quickly. Another key advantage of working with Rambus is that we not only validate the memory subsystem in software and simulation, we also do test chips with the complete PHY and controller. So if you look on the left side, we do the validation first in simulation. We use DRAM memory models from various vendors. We use the PHY model and the controller, so we validate that in simulation. And this is nice because we will give you a complete test bench that you can run your simulations on. But in addition, then we also tape out test chips. So we've done many HBM tape outs, HBM2, HBM2E, and GDDR6 tape outs with the PHY and controller. So we take those test chips and we do full validation and characterization. So this is really good for customers as they're bringing up their systems. They have a reference design or even a reference to look at as they're bringing up their systems to compare our results against their results. And so it's very powerful and gives good peace of mind to the customers that these IPs are up and running. We also have a very nice tool called Rambus Lab Station, and this allows the customers to do bring up and characterization of their specific ASICs. Lab Station interfaces through a JTAG port, and then you can look at just, for example, the PHY and the memory interface. So you can bring up that the physical layer and the DRAM, get that reading and writing memory. Then you can bring in the controller. Then you can interface that to your complete system. So again, very powerful tools that allow you very quick bring up of your system. Now I'd like to take a look at the physical layer of the memory subsystem solution. If we look at the bottom right-hand corner, you can see a cross-section of an HBM system. And starting here at the DRAM, you can see the 3D DRAM. You have the different memory slices connected through silicon vias. And these go out to a micro bump to the PHY on the DRAM. And this sits on a silicon interposer that connects to the SoC. In the blue box here on the SoC, you have the Rambus PHY, and this also is micro bumps. And the silicon interposer typically has 2 2, 3 layers that you can run interconnects through. These are traces. You try to keep these as straight and as consistent as possible for good signal integrity. And then this silicon interposer sits on a package, and that goes into your system. So the PHY has to, and the PHY provider has to provide both the physical layer, the PHY, but also you need to be tightly coupled with the interposer design, because the signals going through in this channel is very important for good system performance. We also have to be concerned about the package, so the signal integrity of not only the PHY but the interposer and the package. And so Rambus has a significant amount of production experience. We started doing this back in 2016, and been through a lot of the learning curves with our customers as they're going through these. These were fairly new back in 2016, so that experience is really helpful today as we're helping new customers who are just doing HBM for the first time by providing a reference design for the interposer and for the package. I already mentioned we have the lab station environment, which helps with the bring up of these systems. Of course, our PHY supports all the latest specifications. The PHY is up to 461 gigabytes per second at 3.6 gigabits per pin. We support all the speed grades, the different DRAM densities, even things like in HBM you have features like lane repair, because you have all these bits running through the interposer, and if one of the bits in a channel goes bad, we can detect that, and then there's extra bits to remap those signals. So again, looking at it both from the IP side, but also from the system side, a complete solution. Although I mentioned the interposer reference design, I want to spend just a little bit more time talking about that. As new customers are coming to Rambus who've never done HBM before, having the interposer and package reference is a big advantage in terms of getting their products out to market quickly. And we've got experience with interposer designs on all the different foundries. There's different 2.5D flows depending on the foundry you're using or the OSAT partner you're using. And we've worked with all of them. So having the ability to know what some of the potential surprises are in doing these new manufacturing processes, we work with our customers and walk them through that. And then even when you get the silicon back, again, how to bring up the 2.5D system and helping them debug and characterize their system. So again, this is a significant advantage. Again, we're not just an IP company, we provide a full system solution. So I've talked about the subsystem, I've talked about the PHY, the interposer, but I want to spend a few minutes on the memory controller. The Rambus memory controller is actually one of the most widely used controller in the market. It's very popular, and it's been deployed in many systems across different types of applications. It's a highly configurable controller, so we work with customers to make sure that we optimize the controller for the features and area they want. One of the main things you care about with your memory controller is your DRAM efficiency. And again, we work closely with customers to optimize the efficiency of the DRAM based on the specific types of data you're running. In network applications, you really care about ECC, so you want to be able to have error correction. So we support error correction in the controller. We also have a significant number of test features in the controller as well. So you've got the test features in the PHY, you've got test features in the controller. So these are all very powerful tools when bringing up your memory subsystem. Now I'd like to dive in a little deeper on our GDDR memory subsystem. If you look at the block diagram, it looks very similar to what you saw for HBM. That's because we deliver our IP as a complete and hardened subsystem regardless of the IP we deliver. If you look at this main difference with GDDR, now on the DRAM side, this is a much smaller interface. It's two 16-bit channels on the DDR interface, or 32-bit per DRAM channel interface. The memory controller blocks again look similar. We have the customizable blocks that are in light blue, along with the GDDR6 controller core. We can customize the interface to the system bus with the AXI, or we have our own custom bus. These can be multi-ported. You have the reorder core blocks, read modified memory block, and in the case of GDDRs, we have what's called inline ECC, and I'll talk a little bit more about that later. As with HBM, the controller is delivered as a soft IP configurable RTL, and this is again configured and optimized to the customer system, both from size of the number of gates and in terms of how the efficiency of the controller is optimized. On the GDDR, we deliver this as a hardened IP that's configured again specifically to the type of system you're implementing. In the case of GDDR, there's not as much configuration. These are JEDEC standard devices, but we are now running these interfaces at very high speeds, so we have to be very conscious of what the board design looks like. And so we work closely with you on all these design challenges. First, I'd like to focus on the GDDR6.5. We start down in the bottom right-hand corner. You can see one of our GDDR6 PCB boards. Under this socket is our test chip, and you recall that our test chips we tape out with both the PHY and the memory controller. This is one of the boards we've done. We did multiple GDDR6 boards, and the reason for that is we want to show the customers what GDDR6 performance looks like with different types of materials. Now that we're running 16 gigabits and even 18 gigabits per second on these traces, we want to look at different materials and show the performance under different conditions. So you can have a very ideal channel or maybe have not such an ideal channel. We have to be able to deal with all those different types of environments. If we move up to the block diagram here, you can see the PHY interface to the controller. There's no real standard interface between a memory controller and a GDDR6 PHY, but we've adopted a DFI type interface. This is used between DDR and controllers and PHY, excuse me. And so we've adopted that interface, and we have that here just in case some customers do their own memory controllers, and we have the ability to interface to those. Some customers will do their own PHYs, and we have the ability to interface to that. So we're still flexible, but again, most companies are looking for this fully validated subsystem. As I mentioned, we're running up to 18 gigabits, the fastest in the industry. We deliver the PHY as timing and hardened close, just like with the HBM. And again, this is really important because it drops into your system without a lot of work on your end. The PCB and package reference designs, this is typically when we engage with GDDR6 customers, this is the first thing they want to talk about is the PCB and the package, because again, not many companies are used to running at 18 gigabits per second on those interfaces. And so taking advantage of Rambus's signal integrity expertise and systems engineering is really helpful to get those products launched. And feature-wise, we support all the JEDEC features, the different speed grades, the different DRAM densities. Another mode in GDDR6 is called clamshell mode. If you recall the chart where we looked at density versus bandwidth, a clamshell is a mode where you can take a DRAM and put it on both sides of the board, so it doubles your density at the same bandwidth. So this gives you, in applications where you need a little bit more memory, you can put a second DRAM access on the other side of the board. And that's what they call clamshell mode. Now looking at the memory controller, the controller core supports up to 18 gigabits per second, and many of the standard features. It supports all bank refreshes. It supports power down. I didn't talk too much about some of the power down modes that we have both in the PHY and controller. These are very important to optimize system power. We have multi-channel or single-channel instantiations of the controller. So again, depending on your performance requirements, you may only want one controller to manage both channels, or you can have separate controllers on each channel. The controller timing is closed at over 1 gigahertz. Again, we're operating at 18 gigabits per second. And the controller has high configurability like the HBM controller. You can interface through AXI ports to your system. We have the reorder core. You can add on memory test as an optional block. Again, this can be customized from both the performance and gate count to your specific system. One other thing we have in the GDDR6 core is what we call inline ECC, and I'm going to talk about that on the next slide. Before I summarize my presentation, I'd like to give you a snapshot of Rambus's high-speed interface IP portfolio. We spent a lot of time today talking about GDDR6 and HBM, but we also offer LPDDR and DDR IP. And LPDDR IP is very popular in some of the same applications as GDDR and HBM. It's used in AI. It can be used for primarily for inference and maybe even some AI training. It's used in 5G at the edge, mobile, IoT. Again, as I talked about earlier, DDR is a very popular interface, and LPDDR is finding new applications as well. In addition to our high-speed memories, we also have a complete line of SerDes interfaces, PCIe with CXL interfaces. Again, these are typically used in conjunction with our memory, so customers will be looking for a very high-speed memory for AI, but then they've got to get the data in and out. PCIe is one of the more popular ways of interfacing the memory, getting the memory in, processing, and then back out through PCIe. We also have network SerDes for Ethernet. For 5G infrastructure, we support GESD and CIFRI, different protocols for those segments of the market for edge. And then finally, we have MIPI. Again, MIPI has been very popular in the automotive market. We offer the MIPI controller, and we work with partners on the PHY. So if you'd like to learn more about any of these products, please go to rambus.com, and we'd be happy to contact you and give you some more details. In summary, advanced applications like AI are driving the need for much higher memory bandwidth systems. This is causing system designers to look at what are the trade-offs and what are the choices they have in selecting the right memory. Today, specifically, we looked at HBM and GDDR6 and what are some of the advantages of these two memory systems. HBM provides you the highest memory bandwidth, which makes it ideal for AI training applications. GDDR6 offers a very good memory bandwidth and better cost efficiency, and so this has been finding its way into inference applications. And so Rambus can work with you to choose the right memory system. As I mentioned, we also offer DDR and LPDDR, so we can look at all the different memory choices as you're trying to develop your next generation ASIC for AI. So thank you for listening in to my presentation, and again, you can reach us at rambus.com if you have more questions.